Yes.
Good afternoon. My name is Dennis Moreno. This is Pedro Surratt. This is Eduardo Cobuchitelli. We're T9-HySol. Our advisor is Igor Suganov, and our industrial advisor for T9 is
Speak up.
from EAC. Our problem statement. So our problem to develop a integral solid rocket booster, an injector valve system that will successfully transition a solid motor into a hybrid motor. Here are some of our design alternatives that we had first explored. These are actually some of the patents that T9 and EAC had developed. We have a non-pressurized tank where the combustion is the source of pressure that goes through a check valve and pressurizes the back of the tank. We had a pop-up valve here that's naturally closed. When the solid motor is extinguished, the pop-up valve will open and allow the hybrid motor to commence. Our proposed design is a two-part aluminum injector with approximately 280 holes. This is for the full-size motor. Tapered hole design to fill with slower burning propellant. Oxidizer chamber to help increase the temperature of the nitrous oxide. Here's our timeline. We had our product formulation early August, September. We're actually towards our final report. We're here in April. We've already turned in our final reports. We're actually planning to do a static firing testing, our final one this coming week. And here's a cost analysis. When we decide to go to a full-scale motor, we'll be looking at somewhere about $15,000 to make the full 12-inch motor. This is including the supplies that's already at EAC. Our current cost of what we've spent so far is approximately $3,000 with all our testing. Our project outputs. Well, we want to make a valve system that reliably and safely transitions a solid motor to a hybrid motor. And we want to publish a journal to the AIAA, and we want to contribute to EAC's goal for breaking the current amateur altitude record. Down here you can see a graph, and basically this is our design output. This lets us know when we're complete with where you can see here is a typical solid rocket booster, high thrust, short duration. Our modified booster will have high thrust, short duration, and then transition to a hybrid motor where it can actually go into a longer duration. So our propellant that we're going to be using is a standard hybrid and solid propellant. We have HTPB is a rubber binder where we have 18% of it. We had a DOA plasticizer, which is a kind of like thins it out, kind of like a thinner for paints. PAPI is a curative. We had ammonium chlorate 400 micron grain, ammonium chloride 90 micron grain, and we actually use metal. In our case, we decided we can either use zinc, magnesium, aluminum, or magnesium, which is aluminum and magnesium mixed together. So we had our mixing propellant procedures. We first determined the actual desired ratio of what we want to do in our pressure chambers. We would combine the HTPB and the DOA, which is our plasticizer, to kind of give us some liquidity. We would add our 400 micron, add our 90 micron, and most importantly, we had to carefully add the metallic fuel because metal going through the air could cause static and potentially could cause discharge, so we tried to keep it down. We were very careful in that step. We had our PAPI, which is our curative. We would mix it, we would vacuum to make sure we can get all the air bubbles out of it, of our mixture, and then we would set it and cure it for 30 minutes. This was actually an alternative design, injector design that we were looking at, and I will have Pedro talk about that.
This is our first proposed design for the injector design. What we did was use a phenolic material tube as our casing. The injector is actually aluminum burst valve. So what essentially is going to happen is, what would happen is the pressure inside the valve, once the propellant and the heat stress units, once the heat of the aluminum failed, and the pressure would pop open the valve, causing the oxidizer to begin flow. After our initial design, we actually completed a SolidWorks simulation using both heat as well as pressure within the tube to see where it would fail or what a projected fail point would be. This is the actual model of our injector valve. As you can see, this is a phenolic tube that would hold the compression fitting and our aluminum burst valve. And here we actually did a pressure test without the solid propellant, just the aluminum burst valve, to make sure that it would hold alone so that it wouldn't release too early. Here's our first injector testing. As you can see, this is the ignition with just the solid propellant. We have our oxidizer tank, which we use nitrous oxide. And once the burst valve would pop open, nitrous oxide would flow. We're using a pneumatic valve. And these are our first set of injector valve tests. As you can see, we had different volumes, different size, amount of propellant we use in each one to get a characterization of a regression rate for our propellant, as well as our valve and how they burst open. You can see here that each individual valve burst inconsistently, so we weren't able to use this as our final injector because with inconsistency in the opening where we can't control flow or the amount of oxidizer into the actual motor. These are different burst times. This would give us our characterized regression rate for our propellant and when the burst time would actually occur. We have our different testings within the previous model. And because our initial injector design is inconsistent, we had to redesign our injector. What we did was come up with a valve system which would open consistently every time. What we did was we sealed at an open valve with a low melting metal. In our case, we used bismuth. Still using our phenolic tube casing for our testing, we filled solid propellant to a known height so we can control, now since we had our regression rate, the amount of time the propellant would take to burn to a certain point, we would know when the metal would melt, essentially opening the oxidizer valve and allowing flow into the system. This is the setup for our first test for this design of our valve. We would use these yellow cords here is the ignition system that would electronically trigger the motor to ignite, as the same oxidizer tank and our pneumatic valve. As you can see here, we have a lot. We did do multiple tests for this as well. You can see as compared to the previous injector test, we have a more consistent opening for every individual test. So we can control and we can predict exactly how much flow is flowing into the motor, how much oxidizer is flowing into the motor per test. And with this, we can actually control the flight time and amount of thrust being produced. Number 6 here in specific, you can see grooves inside, and that's caused because by pouring originally earlier when we mentioned removing of the volume, removing of the air bubbles of the propellant. This mixture, when poured in, actually caught a couple air bubbles, and which causes the propellant to burn at a different rate than actually predicted originally. These are our burn length times as far as the second injector valve, how long it takes for each propellant with a long length of propellant, how long it takes for each burst valve to, for each injector valve to open once melted. This is our final, this is our oxidizer injector design. This allows us to actually test both the propellant, the solid propellant, as well as our oxidizer fuel. We attach our valve system into a PVC pipe, which acts as our fuel system when mixed with the oxidizer. We bottom filled the injector valve with propellant to allow some time for transition period between the solid portion of the rocket, allowing opening of the oxidizer valve, which then flows through the system, which injects oxidizer into the system, and combining with the PVC will actually burn and ignite the oxidizer fluid. These are our initial tests. This first test is with Schedule 40 PVC. As you can see, this is actually the second stage when the oxidizer valve actually opens, shoots oxidizer out. You can see that the PVC provides enough fuel for ignition. This Schedule 80 is actually clear pipe, so we're able to see the flow within the pipe, the motor, and see what kind of flow, whether it's smooth or not. And this is our dissected. This is the one of our dissected motors. As you can see, the pattern of the PVC holding. Now, our prototype test we had to set up a test stand for to be able to measure pressure as well as thrust. In order to be able to do this, we had to set up a data acquisition system and design our motor for our testing. This is our actual prototype that we build from our design. You can see this is our test stand. This is a single piece metal tripod stand. This is our casing, which is made out of aluminum, is our housing. This is where the motor, the oxidizer tank actually sits, and it's held spaced out by a phenolic disc, and this disc allows the oxidizer tank to sit vertically, and all force is pushed down into our load cell pictured here, which gathers our data. This is our data acquisition system. Our load cell feeds thrust into our data acquisition system, which is an Omega 3000. And our pressure transducer actually returns pressure values, which we can in turn calculate the amount of thrust being produced and compare with our results from our load cell. And this is we use for our project. We use Daisy Lab. This is our worksheet, which brings in all the signals from each individual point of data and converts it into available necessary information, which is thrust and pressure.
This is our hybrid motor test. As Pedro mentioned before, the first time we used the data acquisition system. In previous tests, we had only tested that the motor worked. We didn't have any data acquisition system to measure thrust or pressure. Over here, you can see our bulkhead. It's a PVC insert, and you see tubes for pressure gauging. Here you see our valve. Over here, we actually decided to put a liner, which is HTPV. The reason being, we didn't want the solid propellant to keep burning the motor after the hybrid section had passed. So the HTPV prevented that from happening. Over here, you can see our test setup where we have an analog pressure gauge. Over here, we have our pressure transducer that went into the Daisy Lab. For some of the results of the test, the hybrid motor burned for about 13 seconds after it was initiated by the solid propellant. These were some of the expected results that we had calculated at the beginning. A lot of these numbers come from different assumptions and ideal rocket. We did not have an ideal rocket, especially when dealing with the throat size and the nozzle. So these are the actual values that we obtained. Our specific impulse was 33 seconds, and our total impulse was 718 pound-seconds. Yeah, go ahead. This is a graph showing our hybrid motor test result. As you can see here, you see the thrust coming up as soon as the hybrid motor opens. Our peak thrust was 377 pounds. From there, we have our higher chamber pressure at the same time, which was 130 psi. As I said before, the total impulse was 718 seconds. Over here in the graph, you can see how it starts decreasing. Your thrust starts decreasing. It was due to the fact that we had a PVC nozzle and it started eroding. So because the diameter got bigger, our chamber pressure decreased. So over here we have another design that we created after dealing with the PVC nozzle. we decided to use the same rocket motor with our HTPV. What we decided to do with the nozzle was to insert a phenolic disc about an inch thick, and then to add HTPV on top of that. The idea was that we will have a divergent part of the nozzle with the phenolic disc, and then a divergent nozzle in here. As you can see, it's not divergent right now, but as the motor burned, it would create kind of like a conic shape, because it will start eroding the HTPV. This is the results from that motor. Unfortunately, we had failure of the motor in our solid phase. As you can see here, our peak thrust was about, this is not the actual result, it's about 500 pounds of thrust. It was pretty high. We were using Schedule 80 PVC, but it didn't hold. So because of that, we decided to do a more serious motor. So we're gonna be doing a motor encased in an aluminum tube with an aluminum bulkhead and a graphite nozzle. The expected pressure from that rocket is going to be 500 psi because the nozzle throat size was decreased. We're using the same as before, and then the bulkhead actual force will be about 2,100 pounds. This is the bulkhead that we created. Over here you see some SolidWorks analysis that we've done, including heat transfer and pressure. This is our nozzle. As you can see here, we have O-rings. This will prevent the pressure on the motor from coming outside. This right here, it's a holding ring for the nozzle. And then this is our rocket motor. The only thing we're missing right now is to finish up the bulkhead and fire, which we'll be doing over the weekend. And then I want to add that, that's okay.
Okay,
I wanted to add a small conclusion.
go ahead, you have some conclusion?
Well, I wanted to say that throughout the process, you've seen how we've developed our concept from a very small stage aluminum valve. Now we have already a valve that we know that it will work. And currently we're working on our final design. We're going to do a static test before the IAB presentation, and then hopefully after the IAB presentation we'll fly that same motor. So we've definitely accomplished our initial goals.
Okay, so you're 18 minutes, so you're a few minutes over, so bear in mind some of the stuff you're going to add will require an overall adjustment to stay within that 15 minutes, all right? I didn't see cost analysis. Did you present that?
Yeah.
Go back to that for me.